Hello everyone, today we are going to understand what are bounded and monotonic sequences. Firstly, we will start with the definition of sequence. If n is set of natural numbers and x be any set, then a function defined from the set of natural numbers to the set x is called sequence. We need to note here is if we replace this set x with the set of real numbers or subset of real numbers, then we say that f is real sequence. And similarly, if we replace this x with the set of complex numbers or subset of complex numbers, then f is called complex sequence. A sequence is usually denoted by the symbol xn or xn, where f of n is equals to xn is the nth term of the sequence. Let us understand the sequence with the help of example. Example number 1. The sequence an where an is equals to n is, now a1 is equals to 1, a2 is equals to 2, a3 is equals to 3, a4 is equals to 4, and so on to. Example number 2. The sequence an where an is equals to minus 1 to the power n plus 1 is. Now a1 is equals to minus 1 to the power 2, which is 1. a2 is equals to minus 1 to the power 3, which is minus 1. Similarly, this goes on. Now let us understand what is range of sequence. The set of all distinct terms of sequence is called its range. Like in the first example, here the range set is the set of natural numbers itself, and in the second example the range set is minus 1 and 1 only. The next topic to understand is monotonic sequence. A sequence an is monotonic if it is any of the following form. The first form is when an plus 1 is greater than equals to an for every natural number in a sequence, then the sequence an is said to be non-decreasing sequence. And if an plus 1 is less than equals to an for every n belongs to the natural numbers, then sequence an is non-increasing sequence. Third type, when an plus 1 is strictly greater than an for every n belongs to the natural numbers, then we say that the sequence an is increasing sequence. For the last one, if an plus 1 is strictly less than an for every natural number, then the sequence an is decreasing sequence. Let us understand with the help of some example. Example number 3, the sequence an where an is equals to 2 for every n belongs to the natural numbers is 2, 2, 2, 2 and so on to. Here what do we have is an is equals to 2 and an plus 1 is also 2. So clearly an plus 1 is greater than equals to an for every n. Similarly, an plus 1 is less than equals to an for all n. From the first one we can say it is a non-decreasing sequence, and from the second we can say it is a non-increasing sequence. Another example, the sequence an where an is equals to n for all n belongs to the naturals is 1, 2, 3, 4, 5 so on to n plus 1 and it goes on. Here an is equals to n and an plus 1 is equals to n plus 1. So clearly an is strictly less than an plus 1 for all n, implies this is an increasing sequence. Similarly, for example number 5, the sequence an where an is equals to 1 by n for all natural numbers is 1, 1 by 2, 1 by 3, 1 by 4 so on to 1 by n and 1 by n plus 1 and it goes on. Here an is equals to 1 by n and an plus 1 is equals to 1 by n plus 1. The numerator is fixed, that is 1, but denominator is increasing, so we can say that as the n increasing, the an is decreasing. So clearly an is strictly greater than an plus 1 for every n, implies it as an decreasing sequence. Now we need to understand how do we check if a sequence is monotonically increasing, decreasing. Then we have to find a relation between an plus 1 and an. There are three ways to find a relation. The first one is to subtract them. The second one is to find the ratio. And the third one is to find the derivative of an with respect to n. And if we subtract an plus 1 by an, and if it turns out to be greater than 0, then it is an increasing sequence. And if it is less than 0, then it is decreasing sequence. If we can find the inequality here, then it is non-decreasing. And if less than equals to 0, then non-increasing. So is the case with ratio. If we find the ratio of an plus 1 divided by an, it means it should be greater than 1 or less than 1. Here, if the numerator is bigger than denominator, then the ratio is greater than 1, so increasing. If numerator is smaller than the denominator, so decreasing. And if we found the inequality here, then it is non-decreasing and non-increasing. So is the case with derivative. If we find the derivative of an with respect to n and it turns out to be greater than equals to 0, so it is non-decreasing. If it is less than equals to 0, then non-increasing. If it is strictly greater than 0, so increasing. Strictly less than 0, so decreasing. I hope you have understand how we can check if the sequence is monotonically increasing, decreasing, non-decreasing or non-increasing. Let us do some questions here. Question number 1. Find a formula for the nth term of the following sequence. First part is 1 minus 1, 1 minus 1, 1 minus 1 and so on. If we notice here is a1 is equals to 1, a2 is equals to minus 1, a3 is equals to 1, a4 is equals to minus 1. Every odd space or the odd term of the sequence has 1 and even term of the sequence is having minus 1. So we can conclude that the general formula could be minus 1 to the power n plus 1. As we put a1, then it becomes minus 1 to the power 2, which is positive. So clearly an is equals to minus 1 to the power n plus 1 is the general formula for the given sequence. Second part, 1, 4, 9, 16, 25 and so on. This is very simple question. Here we can see is the general formula is n square. 1 minus 4, 9 minus 16, 25 and so on. This sequence looks similar to the B1, but here we can say is that every odd term of the sequence is positive but even term is negative. So minus 1 to the power n plus 1 into n square would be the general formula for this sequence. The next part, minus 3, minus 2, minus 1, 0, 1, 2, 3 and so on. Here we can clearly see that this sequence is increasing, but the first term here is minus 3. So an is equals to n minus 4. We can check here is, if we put n is equals to 1, then a1 becomes minus 3, and if we put n equals to 2, it becomes a2 is equals to minus 2 and so on. The next part is 1, 0, 1, 0, 1, 0, 1 and so on. Clearly this is an alternating series where every odd term of the sequence is having the value 1 and even term is having the value 0. So let us define minus 1 plus 1 divided by 2. Now the first term we need is positive, so it needs to be n plus 1, and if we need the odd term as 0, then we can replace it by minus 1 to the power n plus 1 only, according to the question. Next part, where 0, 1, 1, 2, 2, 3, 3, 4, 4 and so on. Now this is my general formula for n by 2 floor function. The next topic to understand here is bounded sequences. A sequence an is said to be bounded if its range set is bounded. There are further types of bounded sequences. The first one is bounded above. A sequence an is said to be bounded above if there exists a real number k such that an is less than equals to k for every natural number in the sequence. For example, an is equals to 1 by n. Here the sequence starts from 1, 1 by 2, 1 by 3 and so on. So every term of the sequence is less than equals to 1. So this sequence is bounded from above. The second is bounded below sequence. A sequence an is said to be bounded below if there exists a real number m such that an is always greater than equals to m for every natural number. For example, an is equals to minus 1 to the power n. Here the sequence is minus 1 1 minus 1 1 and so on to. Every term of the sequence here is greater than equals to minus 1, so we can say that the sequence minus 1 to the power n is bounded below sequence. The next one is bounded sequence. A sequence is said to be bounded if it is bounded below as well as bounded above. For example, an is equals to minus 1 to the power n. Here each term of the sequence is between minus 1 and 1. So this sequence is bounded below as well as bounded above. So an is bounded sequence. Let us understand how to find if a sequence is bounded or not with the help of some examples. The question is, determine which of the following sequence are non-decreasing and bounded above. The first part is an is equals to 3n plus 1 upon n plus 1. Firstly, we will find if the sequence is non-decreasing or not. Let us consider an plus 1 minus an. Then an plus 1 is 3 of n plus 1 divided by n plus 1 minus 3n plus 1 upon n plus 1. This becomes 3n plus 4 divided by n plus 2 minus 3n plus 1 divided by n plus 1. Taking the LCM, n plus 1 into n plus 2, this becomes n plus 4 into n plus 1 minus 3n plus 1 into n plus 2. After simplifying, it becomes 3n square plus 7n plus 1 minus 3n square plus 7n plus 2. N plus 1, n plus 2. So this start cancelling out and it becomes, here is 4. This becomes 2 divided by n plus 1, n plus 2. This term is always greater than 0. As we start putting n equals to 1 to so on, this term will always be strictly greater than 0 for every natural number. It means an plus 1 minus an is strictly greater than 0 implies an plus 1 is greater than an for every n. This is the condition of increasing sequence. Therefore, sequence an is increasing sequence. For boundedness now, consider an is equals to 3n plus 1 upon n plus 1. If I subtract and add by 3, it will have no change. Now 3n plus 1 plus 3 minus 2, we separate the denominator. It becomes 3 times n plus 1 divided by n plus 1 minus 2 divided by n plus 1. So this is 3 minus 2 upon n plus 1. This term is always greater than 3. Therefore, less than 3. So an is always less than 3 for every n belongs to the natural numbers, implies sequence an is bounded above by 3. Next part, an is equals to 2n plus 3 factorial divided by n plus 1 factorial. For monotonicity, an plus 1 divided by an, it becomes 2n plus 5 factorial divided by n plus 2 factorial into 2n plus 3 factorial n plus 1 factorial. This becomes 2n plus 5 2n plus 4 into 2n plus 3 factorial, and this is n plus 1 factorial whole divided by n plus 2 n plus 1 factorial into 2n plus 3 factorial. This thing got cancelled out and we are left with 2n plus 5 2n plus 4 divided by n plus. So this term is always greater than 1. So we can say here is that an plus 1 upon an is greater than 1, implies the sequence an is increasing sequence. For the boundedness of sequence an, consider an is equals to 2n plus 3 factorial divided by n plus 1 factorial. Now expanding the factorial here, we get that an is equals to 2n plus 3 2n plus 2 into 2n plus 1 and so on to n plus 2 into n plus 1 factorial whole divided by n plus 1 factorial. This factorial got cancelled out. Now we are left with the term an as this one, and clearly this term is unbounded. As we increase the value of n, the value of an is going to be increasing. So an is not bounded above. for the next question, an is equals to 2 to the power n into 3 to the power n divided by n factorial. Checking firstly for the monotonicity. Consider an plus 1 divided by an is equals to n plus 1 into 3 to the power n plus 1 upon n plus 1 factorial into 2 to the power n, 3 to the power n and n factorial. These things got cancelled out and it becomes 6 divided by n plus 1. So this term is strictly greater than 1 for n is equals to 1, 2, 3, 4 and 5 only, but an plus 1 divided by an is strictly less than 1 for n greater than 6. So here what we can say is that this sequence an is increasing, but only up to n is equals to 5 terms only. So the upper bound of the sequence an be the fifth term, which is 2 to the power 5, 3 to the power 5 whole divided by 5 factorial. Now the next question, an is equals to 2 minus 2 by n minus 1 upon 2 to the power n. Let us check for the monotonicity first. Consider an plus 1 minus an is equals to 2 minus 1 upon n plus 1 minus 1 upon 2 to the power n plus 1. This is an plus 1 minus an, which is 2 minus 2 by n minus 1 upon 2 to the power n. So here 2 got cancelled out and it becomes 2 by n minus 2 by n plus 1 plus 1 upon 2 to the power n minus 1 upon 2 to the power n plus 1. Taking the LCM, it becomes n into n plus 1 2 times n plus 1 minus n plus 2 to the power n plus 1 in the denominator and 2 minus 1. After simplifying, it becomes 2 upon n into n plus 1 plus 1 upon 2 to the power n plus 1. So this term is always greater than 0 or positive, implies an plus 1 minus an is strictly greater than 0, implies the given sequence an is increasing sequence. For boundedness, let an is equals to 2 minus 2 upon n minus 1 upon 2 to the power n. This term is clearly less than 2. So an is less than 2 for every n belongs to the natural numbers. Therefore, the sequence an is bounded above by 2. This is all for today, and I hope you have made an understanding with bounded and monotonic sequences. Thank you. Keep learning.